Hi, everyone. My name is Ed Murphy. I'm a software engineer at June Oven here in San Francisco.
Hi, everyone. I am Rahul. I am a software engineer at Google, but I'm representing Donkey, the community here. So.
And this is Donkeycar.
Yeah. If you haven't seen one of these, this is what it looks like.
So we're going to be talking about getting started with self-driving RC car, like Donkeycar. And this talk's going to be in two parts. I'll talk about Donkeycar and sort of the hardware parts of an RC car and how to modify it so you can make it a self-driving car. And a little bit about how you would use Donkeycar to actually go ahead and train the car so it can drive an autopilot. And then Rahul will do a deeper dive into the actual architecture of the Donkeycar open source project and how you might actually modify it to add your own parts. So you start with a regular RC car that you can buy at a store online. Has to be pretty, you know, this car here is a Exceed Magnet. It's about $80. And as you'll see, the one requirement is that it needs to have a separate receiver from what's called the electronic speed controller. The very, you know, if you get a $30 or $40 one, they tend to be combined, and that makes it harder to work with. So once you just take off that plastic top, it looks a lot more like a robotic platform. And the parts that we care about are the steering. So there's a servo in there for steering. There's a DC motor in there, obviously, for propulsion. This particular car is actually four-wheel drive with Ackerman steering, just like your car. The ESC is electronic speed controller, and that takes PWM signals and turns them into thrust for the DC motor and signals for the servo. The receiver takes the FM signals from the RC and turns them into PWMs. That part we're not going to need because we're going to take over deciding whether to go left or right and how fast to go. So we don't actually need the receiver. And of course, the battery, the power supply. So sort of schematically, here's what an RC car looks like. So that RC controller and the radio, that part, and the FM receiver, RF receiver, that part we're not going to need. So we're going to remove those, and we're going to replace it with something else that will deliver those same PWM signals. In this case, we're using a PCA 9685 board. It's like a $5 board, $10 board. It's very inexpensive, but you can use the I2C protocol and tell it to put out a certain PWM signal on a certain channel. And we need two channels. We need one for steering and one for throttle. So this is a very inexpensive way to get a rock-solid PWM signal. And it's very easy to get. Get it on Amazon, get it on AliExpress. And then we need compute. And actually, out of the box, Donkeycar supports Raspberry Pi and the Jetson Nano, the NVIDIA Jetson Nano. So we have build instructions for both of those. People have used other boards. The key thing is that you have a way to communicate between compute and the thing that generates your PWM signal. So for instance, some people have replaced the PCA 9685 with an Arduino. That's one way to do it. Or you can directly use the pins on the Raspberry Pi or the Nano if you so choose. So now we have our compute. And we need to be able to, there's two phases to creating the autopilot. The first one is you're going to drive around because we use a supervised machine learning technique called behavioral cloning. Behavioral cloning is sort of what it sounds like. You take an expert, or I'm not a very good driver, so I'll say expert, and you drive around and you're going to try to mimic that person. So the tag data is actually coming from doing the behavior and recording it. So that's how you gather your data. So we need a way to turn left and turn right, and the easiest way is the Raspberry Pi and the Jetson Nano both. You can both set them up with Bluetooth, and so we use a Bluetooth game controller. And then finally, you need a sensor. When it's driving on its own, it needs to be able to perceive the world. And in the base Donkeycar build, that's simply a camera, Raspberry Pi camera. So it's not even a stereo camera. It's just a regular old camera. And so that's all we need schematically to modify the hardware to create a self-driving car. And when you're done, you get one of these. And this is a 3D printed part. The project's all open source, from hardware to these 3D printed parts to all the source code. So you can print this thing yourself, or we have a store for your convenience, so you can just sort of buy the part if you don't have a 3D printer. And we have detailed instructions on how to put this all together. And probably everybody in this room is pretty hardware handy, but if you're not, you don't have to worry about it, because in the base build, there's no soldering at all. It's all jumper wires. And this is race tested with lots of crashes, and it's very, very solid. So now we have our hardware. Now we want to get ready to create an autopilot, so we need our data. So we're going to go drive to do the data. We're doing behavioral cloning, so we're going to clone the person that's doing the driving. And the way this loop works, this is a flow chart about basically the way the drive loop in the Donkeycar software works. Is when you first start up, you'll initialize the hardware. In particular, you need the camera to be ready to be able to take frames. And then it will go into a loop. And by default, it's going to go 20 hertz. And the first thing it's going to do is going to take a picture. 160 wide, 120 high RGB picture. And then the next thing in the data pipeline is it's going to go read the steering and throttle. And now you're driving it, so it's going to go read that steering and throttle from your game controller. And it's going to normalize it to for a range from -1 to 1, left to right, 0 being straight. So we have all normalized values. And then it's going to take those normalized values and going to turn them, it's going to write into the hardware. And what that basically means is we've calibrated the car so we know what full left, full right, and middle is in terms of PWM values. So we're going to convert that normalized value into a PWM value, and then we're going to send it over the I2C bus to the PCA 9685, and it's going to start generating the PWM signals, and therefore the DC motor is going to get the right throttle, and the servo is going to have the right steering angle. And now, because we're recording data, now we save that data to the SD card. And we're going to do this 20 frames a second. So basically, you're sitting there, you're driving your car around the track, gathering all this data, and hopefully it's all good data. So the data looks like this. When each of those times through the loop, it's going to save the image, so what the camera sees, and then what you told it for throttle and for steering. So it says, so basically it's saying, the car saw this and the human said to do this. So we save these values. So you can see on the left-hand side here, driving pretty straight, so the angle's around 0. And here on the right, going to the right, so the user angle is 0.5. Now, another way to gather data is to use our simulator. So we have a really good Unity-based simulator. So you can do a lot of your practicing in the simulator. And you can even use this data if you want to combine it with real-world data to get larger data sets. One thing, especially when you're driving the real car, is you're going to make mistakes. Even good drivers make mistakes, but often you'll be on the track with other cars. And they're going to crash into you, you're going to crash into them, you're going to have some bad data. And we have ways of, while you're driving, to say, hey, forget the last 10 seconds of what I did. I think there's a Black Mirror episode like that, too. Like, just forget the last 10 seconds, and let's move on. So we have that feature. But also, you can go back and treat all of your data like a movie. And so you can just cut out sections of that movie and the steering and throttle associated with that and clean your data. And clean data is very important because you're collecting all the data. It's not a data set that you're going to get from the internet. And so you're never going to have as much data as you want. So you want to make sure the data that you do have is really clean. So now we build our hardware. We've got a nice, clean set of data. Now we want to use that data to train an autopilot. And we're very flexible on autopilot. So we support a number of different formats. By default, a regular TensorFlow H5 model. You can also take that and create a TensorFlow Lite model that will actually infer faster on the base, like Raspberry Pi hardware. You can use TensorRT. So with the Jetson Nano, where you have a GPU, TensorRT will use the GPU, and you'll get much faster inference. And then finally, Google Coral Edge TPU, we can use the Coral Edge TPU compiler to create a model for that device that will infer very, very quickly. And we have a number of different model architectures that you can use, network architectures. And the default one, and really mostly everybody uses this one, is a linear model where we have linear outputs, so continuous outputs of throttle and steering. So again, those normalized values from -1 to 1. We also have categorical model where you can bucket into categories your output, like really left, sort of medium left, straight, medium right, all the way right. And the categorical model actually performs a little bit better in certain situations. We have a model that will, where you can include inertial measurement unit data to help isolate you a little bit more from the details of the room. And then we have a couple of models that will actually use some of your past behavior to help predict your future behavior with an RNN in a 3D model. And we have a number of other experimental models. The key thing about the Donkeycar software is that it's setups for you to experiment. It's easy to use out of the box, but you have all the source code, and it's a really great test bed for you to test your ideas about autonomous driving. And in a very safe way, because you're working with a 1/16 or a 1/10 scale car, you're not going to hurt anybody if you run into them, unless you go as fast as sometimes we do in our races, so it starts to get a little scary then. So you never have as much data as you want, so you want to make sure your data counts. And so we have ways of sort of stretching your data. So one is, it's very easy to do data augmentation. I would definitely suggest that whenever you train a model, just use data augmentation. It's going to take the frames that you already have, and it's going to modify them in a way that still will make sense. It would make sense to you. It should make sense to the neural network. We have filters that will add noise, shift colors, add false shadows. And one of the things when you're doing camera-based autonomy is lighting conditions have a very, very strong effect on the neural network. So the more that you can vary lighting conditions on the way in, the more generalized you're going to be, the more stable you're going to be in different lighting circumstances. Now, another thing, if you saw that data that I showed before, I have the horizon in there, and above the horizon is the walls and all the chairs and everything. So the first time I trained my car for a race in that room, I got there early, I trained, I got lots of data, and it worked really well. I was really pretty excited. And then race time came, and the room was full of spectators by then. And then they said, go, and my car just didn't do anything right. And what happened was when you actually, and I'll show you one of the ways that I figured that out, but it was seeing everybody's legs that wasn't in my data, and it thought, that's important. That part of the image that I'm looking at is important. And so the way that I handled that was I used a feature that we have for cropping out and just keeping the region of interest that you care about and cropping out stuff that should not be important to the network. And then finally, you can do transfer learning. So we have a model, we have a pre-existing model with lots of different tracks. You can start there if you want. And Rahul will talk a little bit about, he's using an ImageNet model as a starting point as well. So now we're training our model, so is our model working or not? So we have a number of ways to help you see that. And the first thing is just, we plot model loss when you're as soon as the model's calculated. And you can see here on the left, without data augmentation, it's a little bit overtrained. The training loss is much lower than the validation loss. But with augmentation, where we have a lot more variation, the training and the validation loss are very similar, and that's a good sign. Oops. Okay, and then, so more training. I'll just do the visual part of this. So one of the tools that we have this is really useful is, remember that we're doing behavioral cloning, so we want the car to behave like the person that drove it to get the data. So tubplot is a utility that will take a random 1 second of the data that you collected and then do inferences and then plot it against what you really did. And you can see this top one is steering angle. And the orange line is the predicted line, and the blue line is the real line. You can see the orange line doesn't go as extreme as the real driver's line, so it's under-predicting steering a little bit. And then the bottom one is throttle, and you see the orange line's consistently above the blue line. It's over-predicting throttle. Rather than retraining, we actually have some parameters that we can set after the fact to try and tweak this kind of behavior and get them closer together. But this is a good way to see, and you'll see if your model's not going to work at all, you'll see it when you look at this plot. So the other thing to look at is just what is the neural network activating on. So we have a utility to be able to show an image and overlay the parts of the image that are triggering the neural network. And this is an example of what you want to see. So there's the dotted line down the middle and the 2 lines on the edge, and those are the things that are being activated. It's seeing the track, right? So that's what you want. Here, there's a glare on the track, and the neural network's really seeing that glare. And that's one of the things that can really throw you off. And data augmentation can help. There's some physical things you can do in the car. Put a filter in front of the camera to try and filter out some of this glare, like you would when you're driving your own car with a pair of sunglasses. But this is a great utility to use to figure out, hey, why does my neural network, when I'm on this part of the track, have that odd behavior? Okay, so now we figured that all out and we generate our thing. Now, we want it to drive itself. So let's do that. And what we do to drive, if you saw Chris Anderson's keynote earlier, we're part of the DIY robocars community, and we like to race. So we race in Oakland once a quarter, and they're sort of, you build up to these races and you optimize everything for these races. And so when in the autopilot, it's very similar to the data collection loop. You're going to initialize the hardware, you're going to take that picture, but now instead of getting the steering and throttle from the controller, you're going to get the steering and throttle by inferring it through the neural network. And then you're going to write it to the hardware. It's going to turn it to PWMs, and you're going to set those into the hardware. The first race here is actually Rahul and I, because our cars are both Donkeycars, are both very similar, and the idea was to match race very similar cars. And what happened was my car just, and here I haven't yet completed a lap in DIY robocars races yet. Not yet. I've been to 3 of them so far, not completed a lap. So I'm so excited. I have so much data. It's working great. I've got the cropping. I've got the augmentation. He says, go, and my car just goes in a circle. Just literally just drives in a circle. And I picked up the car. I'm like, I don't know what's wrong. And I looked, and the lens cap is on. And so it was just getting a black frame. And if you see the track's mostly right. And so the neural network's like, probably right. So it just kept going in a circle. And once I fixed that, then we had a great race. And so that was the first time I made it around the track, and I ended up second in my class that time. So the next part of the talk is actually more of a deep dive into the actual architecture and source code and how you might use it to actually try one of your experiments.
Right. Thank you, Edward. So you've looked at the hardware, so let's talk about some of the software. So Donkey is ready to go from the ground up. So when you build your car and you don't want to mess around with the software, it just works. But if you want to customize it, that's when things start to get really interesting. So it's really important to understand how the source code has been organized if you want to mess around and you want to modify some stuff. So if you actually clone our repo, this is what it'll look like. On the right, you'll see a bunch of contributions, and then you'll see something called parts. And the entry point is something called vehicle.py. Most of the source code is in Python 3 and uses TensorFlow and Keras for building the machine learning models. And the vehicle.py is an aptly named entry point. Vehicle has a bunch of internal state, and that's what represents what the car is doing currently. And parts essentially contribute to that internal state. And a part is something that has a well-defined input and produces something usually. So let's look at that in more detail. All right, so this is what the vehicle class actually looks like. So here, as I said, there's some memory involved, and so that's the internal state of the car. And let's see what adding a part looks like. So when you add a part, we'll print the part that's being added, and then we'll usually spin the part in its own thread. And that's usually because you don't want slow parts to make everything else slow. So if you did not run every part in its own thread, then you could have a slow part that would affect the entire car, and the car would be slower. And so essentially what we do is we create a daemon thread, and we keep track of that thread on your behalf, and then we add that part. So the important thing is that we create a thread, and then we keep track of that thread. So adding a part is pretty straightforward. And then when you start the car, if those threads aren't already started, we'll start them, because that's when those parts will start contributing to the internal state of the car. And then we'll have a loop count. That's because we want the car to run at a steady frame rate. So usually a Donkey runs on a configurable frame rate. Usually it's 20 to 30 hertz. Sometimes it can go as high as 60 if you have the compute available. So in this case, your while loop is going to run a lot more frequently than the frame rate. So we'll just introduce delays and sleeps, so the car runs at a steady frame rate at that time. And then so most of the code that you're seeing here is actually the sleep, the code to sleep. There's one call to update parts, which we'll look at in more detail. So when you update parts, essentially all you're doing is, as I said before, parts have this well-defined input. And so we take all the existing inputs from the vehicle's memory at this instant in time and give it to the part. And the part will evaluate what it wants to, and then produce a bunch of outputs. And so run-threaded is the API to do that. So once the part is running in its own thread, we'll send in those inputs every frame, and then we'll produce a bunch of outputs. And then finally, we'll save those outputs into memory. So essentially, what's happening every single frame is we're taking a snapshot of memory, giving it to the parts, and the parts produce more data, and then they contribute back to that internal memory. And so we build internal state going forward every single frame. And then finally, when it comes to stop, we'll just ask the part to shut down. At that point, the parts are no longer running, the threads are shut down, so the car can come to a halt. So you looked at things from the perspective of the vehicle. Now let's understand what the part is and what fundamentally a part does. So, well, this I already talked about. So here's an example of an OLED part. So this actually came off a personal necessity. So Donkey doesn't ship with any OLED displays. So I started racing Donkey around a year ago, and I used to make a lot of mistakes when it came to racing. So the most common mistake that I would make was I would go to collect data on the track, and I would have like 20 perfect laps around the track, and I'd be very happy with myself, saying, "Oh my God, I got some great data. The model's going to look great." Only to my dismay, when I came back to my laptop and when I was trying to copy data, there was no data. I was like, why did that happen? That's because you need to put the car in recording mode. If you don't ask the car to record any data, it's not going to. And then I smacked my head. I'm like, oh no, like I lost all that valuable track time. So I'm now going to have to repeat all that. So one of the key ways I wanted to fix that problem was to build an OLED display which showed the current state of the car, what mode it's running in, how many records I have, so I don't make the mistake going forward. So here I have a simple part. It's going to talk to an OLED display. And run, when the run is invoked, which happens when the thread is started, it's just going to turn itself on. And run threaded API is the important API. Remember, the vehicle calls the run threaded API when it's time to update the state of the car. Here it's actually getting 3 inputs. It's getting the current state of recording, the number of records that it has already got, and user mode. User mode is when is a way for Donkey to know whether it's the user driving the car or whether the car is on autopilot. So these are the 3 things that I want to keep track of in this part. And then shutdown is when it just sets itself to false. So it basically knows that it needs to shut down. Now, once you define the part, here's where things get really interesting, putting the vehicle and the parts together. So now I create a new instance of vehicle. I create an instance of the part by passing in the I2C bus number, and then I add the part. At this point, what's happening is I'm passing those in 3 inputs. So I'm telling the vehicle that this part expects 3 inputs, whether the car's currently recording, the number of records in the data store, and what the mode is for the car. And then once the vehicle knows that these are the inputs that the part needs, it will call run threaded with those 3 values in the run threaded API. So that's how these parts are put together, and they form a beautiful data pipeline. So you can have completely decoupled producers and consumers of data, and the vehicle just knows how to connect them depending on what the registration mechanism is. And so now that you know the general architecture of Donkey and you understand what vehicles and parts are, we'll talk about the approaches to self-driving. So if you've been waiting for, hey, can you show me some machine learning models? This is the time. It's time to wake up, and now it's time to start paying attention. So the default model in Donkey is called the Keras linear model. A lot of racers have put it to really good use, and even people who've won use this model by default. It's a really simple Keras model. It takes the image input. So image, as Edward showed you before, is usually of the size 160 pixels by 120 pixels in 3 channels, RGB. And then you define a convolutional layer with a filter size of 24 and the kernel size of 5 by 5. And you vary the filter size and the kernel size a couple of times, and you intersperse it with some dropout layers to prevent overfitting. If these things sound a little different and you are not familiar with these terms, these are pretty standard machine learning layer types, and this is how you put together a deep learning network, and you define this acyclic graph of layers. And so once you repeat these layers, then finally you get to the interesting parts. Now you want to flatten the output of all the previous layers by using a flattened layer, and then finally you end up with a dense layer, which is a fully connected layer of 100 nodes, and then you introduce dropouts to prevent overfitting again. And finally, it comes to define outputs. So when you define outputs, there's 2 different outputs you want. This first one is the steering, and the second one's throttle. So you define one output, which is a dense node with an activation function of linear, because you want continuous values, like Edward described. And then finally, you put together a model with the image input and the defined outputs, and there you have your graph correctly defined. And now, Keras linear is just a part. It's a part that consumes the input image and produces 2 values. It produces steering and throttle. So here, notice I'm calling the function I previously defined with the number of inputs S2 because I want steering and throttle, and then I'm calling compile. Compile, all it does is it asks Keras to perform some validations on the graph, and then here I'm specifying a loss function of mean squared error. So Keras will use mean squared error to compute if the network is actually learning or not. So it'll tally the predicted values for steering and throttle versus actual values, and it'll compute the distance between those values. And if the distance gets smaller, that means it's learning something. Finally, it consumes the input image array. We reshape it. We'll call predict on it to get the outputs. And then once we get the outputs, steering and throttle are just the first and second ordinals in the array. So it's pretty straightforward. And finally, once we have the steering and throttle values, we can write them back to the PWM driver like Edward showed you before, and then that's how the car gets controlled. So I showed you the basic Keras linear model, but there's a lot of other Donkey models like Edward showed you. But there's also a lot of experimentation that we are currently doing. So far, all the machine learning models that we talked about are actually fairly small. And that's mainly because we don't have that kind of compute on these cars. So far, we've been using Raspberry Pis and Jetson Nanos. The Jetson Nano was a huge improvement for us because that was the first time where we had a SoC with a GPU on board. So the Nano has 128 CUDA cores, and we got TensorRT. which helped us do inferences at more than 60 hertz. However, when we experimented with deeper neural networks, like I did with, for example, if you use a VGGNet or a ResNet-based backbone with ImageNet, then you start running into some computational challenges. So you go over your frame budget very quickly. Remember, for the car to self-drive itself nicely, you need to meet a frame time of at least 30 hertz. Otherwise, it's not just going to do well. So when I experimented with the deeper neural net, I was on a Jetson Nano. I was only be able to hit 16 hertz, which is not good enough. So in the future, when NVIDIA decides to release their new chip, which is 20 times better than the current Nano, sometime in the future, like I think the expected date is March, then hopefully we'll be able to run our deeper neural net. But again, this should not stop you. The Jetson Nano is actually quite capable of running a deep neural net, so you can actually mix and match what you have. So I just also want to talk about the role of computer vision in Donkey. So there's two different schools of thought for where computer vision should play a role. And the first school of thought is where they use computer vision alone to solve self-driving. So these are similar to line-following robots, where usually tracks have a central yellow line, and they'll just follow the color yellow by using an HSV filter, or they'll do Huff transforms on the lane to do lane following. And that actually works pretty well. We also have some very interesting approaches, like Chris showed off, which is cone slam, which computes visual odometry based on the patterns in the ceiling, which are predictable in an indoor setting. I am more interested in the role of computer vision when it comes to deep learning. So one example is data augmentation, where Edward showed you how data augmentation can really help the model generalize. And then we can also do a lot of image pre-processing to normalize the image to help the machine learning model do the right thing. So let me show you an example of that. So here's an example where we had a real problem. So Donkey, even today, is still very susceptible to changes in the brightness in a given scene. So this used to happen a lot. So I used to go to a race. I would train in the morning, and I'd be feeling pretty happy about how the model's doing. And suddenly, someone decides to open a window, and then there's glare on the track, and that completely throws off the model. And that's pretty bad as far as racing is concerned, because it just complicates matters. So what I was looking at possible solutions, and having done some image processing myself back in the day, I realized that if we actually did some image contrast enhancement and normalized the image before we fed it to the machine learning model, that might actually solve the problem. So if you've done image processing before, you might be wondering, saying, isn't this just histogram equalization? Isn't this really a solved problem? Yes. However, because we have to meet the 30 hertz frame budget, histogram equalization is actually quite computationally intensive. The best implementation of histogram equalization on OpenCV can only give you 10 hertz, which is not good enough. So I found this paper, which is fast contrast enhancement by adaptive pixel value stretching. This was a paper that was authored in 2018. I made an implementation using NumPy's vectorized arrays and got it to be really fast. And these are some of the results. So I don't know if it's clear on the projector, but on the image on the right has more pronounced edges, and the image is more normalized. And edges are really important when it comes to neural nets, because edges are used to build higher level features and higher level image understanding. So this is an example where an image processing algorithm and a computer vision approach can help deep learning. And so, and if you're not familiar with the image, this is Lena. This is what a lot of image processing experts will use to show off their filters and show off new algorithms. So this was my first results. And then, because Donkey is so open for experimentation, you should not be restricted by what's already out there. You should be, you should be open to experimenting with new ideas. So feel free to clone the code base. And if you have any questions, we usually are available on the Slack channels, and there's a lot of help out there. And people do some really interesting things. And so if you have ideas, you should play around with it. It's not that hard. And then thank you for listening to us. If you have questions about how any of this works, we are on the Slack channel, as I said before. It's donkeycar.slack.com. And we have extensive documentation on docs.donkeycar.com. And our next race is on December 7th. So if you're in the Bay Area and you want to check out one of these races and see what it's like, feel free to come to the Oakland circuit launch campus. Thank you.
Thank you.